and with his the basic ideas and the methodology of teaching this course, uh, we are also trying to have this the similar course running for our UG course students as well as for PG students. PG thermal as well as PG automotive. This course we run for them as a compulsory course, and for UG students we run this as an elective course. So it's a good course, and definitely it helps for the development of our own the software. I will say the software which is instead of using the other software. If we go through this basic course, we can learn to develop our own software, and which is definitely useful for the understanding of our basic understanding of this course. And definitely later on we can have the use this course, the use of this course can be useful to take into the what are the softwares are available. Let us, if you take the ANSYS, so even in ANSYS Fluent we can write our own code, and that code can be useful as a user defined function in the ANSYS, and so that's the base for this course. So as it has been discussed that the governing equations are supposed to be the part and parcel of this course. So in the if we see the basic governing equations for the in case of computational fluid dynamics, is are supposed to be with related to the conservation of mass, momentum, and energy. So we are supposed to be considering for the from the derivation point of view. So my today's the presentation will be with related to the how we can derive it from the very simple aspect, and then in the next lecture I think I have to consider for the conduction problem. So as all of you are aware, the I have already shown here that these are the three basic the equations, that is mass, so balance of mass, so mass flow rate on the surface of the control volume has to be balanced. So incoming mass and outgoing mass, that has to be balanced. Then momentum. So using the second law of motion, Newton's second law of motion applied to the control volume. So rate of change of momentum is equal to the net forces acting on the body or in the control volume. That is what is supposed to be the second important and most important, and that is based on these two are we consider as a Navier-Stokes equation. And third one, which is more useful to us when we are dealing with the conduction equation, that is the energy equation. So I am dealing here particularly for the more towards on the heat conduction, advection, and heat generations. These are the three part of it. The energy equation, again, it's again the based on the conservation of energy. So this leads to for the derivation. So we'll have to information why we want to have this. We want to know the point by point information about the velocity, pressure, and temperature in the given domain. Now I mean domain here is the control volume. What is the region? What is the specified region or space or the volume which we have considered our the study area, and in that study area we want to derive this. So what is the approach for this? We employ the balance statement, very basic statement we supposed to be considering here. So employing a very elemental control volume and applying the very basic balance statement for this. So what is that statement? The statement is balance statement of the for an elemental control volume. And basic statement which we are dealing is a very simple as such. It's with related to the rate of accumulation of mass or momentum or energy is equal to the rate of inflow of mass, momentum or energy minus rate of outflow of mass, momentum or energy plus rate of increase of mass, momentum or energy due to some source. So for understanding of this, I have taken here the elementary control volume. So this is my elementary control volume. This is delta X and this is delta Y. So in the X and Y direction, I have here delta X and delta Y, which is supposed to be considered there, are supposed to be taken here. Okay. So using this, the distance in the X direction and distance in the Y direction, delta X and delta Y, I have supposed to be here. Okay. So for this delta X, delta Y, I have considering here two-dimensional, so that it can be easy to me for understanding, and then I can extrapolate it for the third direction. Now, as far as when we are considering it two-dimensional, the third direction we are assuming is a unity. So the one direction we consider delta X distance, in the another direction, in the Y direction, we consider delta Y distance. So the control volume which I have here is delta X into delta Y into 1. So volume which we are considering here for this control volume is delta X into delta Y into 1. And for this given control volume, depending on the equation, the first equation, if I consider for the continuity equation, so I will have the rate of accumulation of mass, then the rate of inflow of mass, and then the rate of outflow of mass, and then if there is any rate of increase of mass due to some source. That is what is supposed to be, we have to take into consideration for the case of the continuity equation. Similarly, if I want for the momentum equation, the rate of accumulation of momentum will be equal to the rate of inflow of momentum minus rate of outflow of momentum plus rate of increase of momentum. And similarly for energy. That's the way. This is the basic statement. And if you remember this, and it is not very difficult. So accumulation in the control volume. So this control volume which we are dealing, in this control volume, how much is the mass, momentum, or energy is accumulated is equal to incoming, maybe from both axes, both direction it can be incoming, or maybe incoming from three direction, going in out in the one direction, or whatever maybe. So incoming and outgoing, that the efflux of that incoming and outgoing, that we have to take into consideration. And lastly, if there is the increase. That's a very basic statement, and this basic statement is used for the derivation of this. So we'll see it for the cases one by one, how it is supposed to be useful. So conservation of mass. So I have considered here that for the simplicity of my understanding, from the left hand side and from the bottom side, so I will call it the west surface and the south surface. Mass incoming is m dot x and m dot y in respect x y direction, and it is leaving the control volume the north and from the south as the east, that is m dot x plus dabba m dot x dabba x delta x, and north direction m dot y dabba y dabba y delta y. Okay, these are incoming flux outgoing of the through the control volume. Okay, so incoming minus outgoing, that is what I am supposed to be up. Now if you see that in the previous statement which we have, what we have considered that the rate of accumulation in the control volume. So my mass of control volume, what will be the mass of control volume? The mass of control volume will be rho into delta x into delta y into 1, right? Because it's so multiplied by 1. Okay, so why I have supposed to be considering it is multiplied by 1? Because I have taken here the case of the two dimension. If I supposed to be have the third direction, it will be delta z. Okay, so mass of control volume will be density multiplied by volume, and that's why here I have supposed to be taken as a rho into delta x into delta y for this control volume. And that is what I have considered here. This mass of the control volume increase or decrease, whatever may be happening with respect to the time. So rate of accumulation. So this mass of control volume, that is rho delta x delta y with respect to time, is accumulated in the control volume. That is what our the left hand side. And right hand side, we suppose we have the influx. So influx m x, these are two incoming and outgoing of these two are there. So if I consider there the total influx, inflow and outflow, so this and this get cancelled, okay, and this get cancelled. So what will be remain will be the minus of these two, as the these are to be on the outgoing side. So incoming minus outgoing. So these are two are negative on the right hand side. So minus m dot x dabba x delta x minus m dot y dabba y delta y, plus what is supposed to be we expect here is the plus of any increase due to any increase in mass due to any source. But as far as the conservation of mass is concerned, this is supposed to be equal to 0. So there is no any increase or there is no any, as far as the our general flow considerations are taken into consideration, this is not there. So this is plus 0. Okay. So then I can supposed to be put the values of this. What is m dot x? M dot x is but the rho AV, right? So rho is the density, A is the area, and what is delta y only? Because at this surface we are considering delta y into 1 is the surface area at this face. Okay, so delta y into 1 multiplied by the velocity incoming in the x direction, that is u velocity. So rho u delta y is m dot x. Similarly, rho v delta x will be the m dot y. So if I put these values of this m dot x and m dot y here, I will get it in the form of the dabba rho by dabba t is equal to minus rho u dabba x minus rho v dabba y. Okay, I have just put all this there and then simplify it by considering all this the definitions of this mass of control volume, mass inflow in the x direction, mass flow in the y direction, and mass outgoing in the x direction, mass outgoing in the y direction. So if I put all this there, I am supposed to be how the equation is like this. And then these negative signs which are there on the right hand side, if I bring it on the left hand side, I will have the equation that is dabba rho by dabba t plus dabba rho u by dabba x plus dabba rho v by dabba y. If I want the third direction, it will be dabba rho w by dabba z is equal to 0. So that is what the differential equation which we can consider derived by using this simple statement. So this basic statement, we have to always remember this statement, and based on this statement, we can have this is the governing equation. Okay, so this governing equation which we are considering, or the so what these terms are supposed to be. So dabba rho by dabba t is the change of density, or what we can say the mass per unit volume. The density is nothing but mass per unit volume. So change of mass per unit volume with respect to time. This is what the inflow minus outflow of the mass in the x direction. This is in the y direction. So if I want to simplify it and put it in the vector form, this can be further simplified in the two ways. One way we can consider dabba rho by dabba t plus del dot rho v is equal to 0. Or if I further explore this, the rho u, we further explore this rho u and this rho v as supposed to be the products. So we can explore them in the two parts. So rho, considering one constant and keeping the derivation of others. So like this in the both of the case, and we will have this, the 5 terms will be there. And this 5 term, if I again simplified, one in the form of the total derivative. So this is d rho by dt is the total derivative of the density plus the terms which are remaining there and I keeping that rho is a constant, then rho W by W X plus W rho V by W Y is equal to 0. So this is formally another form of this equation, and which we also supposed to be considered to be written as d rho by dt. This capital D is indicating the total derivative of density plus rho del dot v equal to 0. And if I want to simplify this again for different cases, we can also this. There are two ways. One is like this, we can also express it. Another way is like this, we can also express it. So both ways we can explain this, the continuity equation, which is nothing but the conservation of mass. The another way, which is more commonly used from the integral equation form. So using this RTT equation, so the volume integral term of the control volume with respect to the control stationary mass system, and then this is what the again for the surface inflow of this with the RTT equation. I am not going in much details of that. You have supposed to be considered it in the fluid mechanics. So the Reynolds transport theorem, RTT equation means Reynolds transport theorem. And using this base equation, we can also derive it on the similar line. So by using this Leibniz rule and divergence theorem, we can again get it in this form. Okay. So basic equation which we want that is supposed to be the total derivative of density plus rho del dot v is equal to 0. This also can be defined from using the particle definition. So these are the different ways. So for incompressible flow, when we say the incompressible flow, we know that the density is constant. And for the constant density, d rho by dt, that is the total derivative of density is 0. And that's why the term which is coming there, that del dot v is equal to 0. And this del dot v, if I want to use it in the Cartesian coordinate system, can be w by w x plus w v by w y plus w by w z is equal to 0. And this is what more commonly we are using when the Navier-Stokes equation we want to solve. So what are the problem we generally consider in case of this is the lead-driven gravity problem or a flow through the pipe or something, and there we use or two-dimensional or three-dimensional, and in that case you will have w by w x plus w v by w y is equal to 0. And that is the basic equation. If I want in the stream function, we can also use by using the basic definitions of stream functions, and then we can also write it in the form of that, in the form of stream function by using the definition u is equal to delta psi by delta y and v is equal to minus delta psi by delta x. And we know for the streamlines dx by u is equal to dy by v is equal to dz by w and so on, and then we can put it there, and then you will get it in the form of the steady state equation. So this is what about the continuity equation. If you have any doubt, any question, you can ask me for a short while. Anybody? Okay, I assume that it is known to all of you, or all of you have understood, or I don't know whether I am able to give you some inputs or not. Okay, I consider that this is what the way we can derive the continuity equation. Then we will move for the momentum equation, and we are taking here the linear momentum equation. So linear momentum equation, again on the similar principle what we have done for the continuity equation, we are considering here for the momentum equation. So again, the mass incoming in the x direction is m dot x, mass incoming in the y direction is m dot y. Again, we have considered these four phases for this control volume: west phase, south phase, east phase, and north phase. So this is for the incoming of mass, and this is what I have supposed to be represented here for the momentum. So momentum incoming in the waste surface, there are two momentum incoming in the waste surface. So that they are supposed to be represented. I am using the term P here. So P dot I am considering here for the linear momentum. So P dot X is a linear momentum in the X direction. Okay?
Sir.
And P dot Y is the linear momentum. Yeah.
Hello. Sir. I suggest you to you are using cursor, I think, while yeah, I suggest you to right click if you are in the full screen mode.
Yeah.
Right click on your PPT and go to pointer option and select the laser pointer, because this routine pointer is
that is there.
You are using laser pointer.
No, I am using the actually on the PPT there are panes.
Okay, because this is visible. This is visible now. Yeah, please go ahead.
So on the waste case, if we see, there are two kinds of the momentum coming into the picture. One in the normal direction, another in the tangential direction. So this P dot X is in the normal direction along the waste surface, and in the tangential direction it will be P dot Y. So these two are represented on the waste surface, and that's why it's shown there, the P dot XW and P dot YW. Okay. On the similar line, for all these four the faces, we have in the normal direction, this will be P dot Y at the south surface in the normal direction, and in the tangential direction is P dot X at the south surface. Similarly, on the east surface, we have the outgoing is P dot XE, and the normal will be the P dot YE. And on the similarly, we can consider here on the east surface. So if I suppose to be consider these four to be represented here, so what will have that the m dot x into u be nothing but the momentum in the x direction. So it is the mass incoming in the x direction multiplied by the u velocity in the x direction, and that's why it is a normal to this surface, okay, the waste surface. And as we are dealing here, so m dot x, as we have already defined, what is m dot x is the rho a v. So it is rho density, area will be delta y into 1, as this area is delta y. So delta y into 1 into u velocity in the x direction. So rho u delta y is the mass flux incoming in the x direction. So it is mass flow rate, that is m dot x multiplied by u velocity, and if I put it together, I will have rho u delta y. Similarly, for the m dot xv, this is what at the waste surface again, which is supposed to be because of v velocity. So mass incoming in the x direction is m dot x. For this x direction, mass flow rate is m dot x. So if you see on the waste surface, both these are supposed to be m dot x, m dot x. Then in the normal direction, u velocity coming into the picture. In the tangential direction, the v velocity coming into the picture. So this momentum is the normal momentum. This momentum is a tangential momentum, which is in the x direction. Similarly, in the y direction, this is what we are supposed to be considering now at the south surface. So m dot y into v, that is what in the normal direction. This m dot y into v will be in the normal direction. So you'll have rho vv delta x. So the mass in the y direction will be rho v delta x into 1 multiplied by v. That is what in the normal direction in the y direction. And this is what the tangential direction in the y direction. And this is because of u velocity. Here it is because of v velocity. Here it is because of the u velocity. Normal direction is here is the v velocity. Normal direction here is the x velocity. Okay. On the similar line, if I want to represent it in the outgoing side, so on the outgoing side, we have the east surface and north surface. So again on east surface and north surface, so there are again two. So P dot XE and P dot YE. So these are supposed to be incoming plus. So what are there of the incoming momentum plus will have the plus dabba of P dot XW by dabba X delta X. Okay. And this I can suppose to be further explored it to be equal to rho UU by delta Y plus dabba of rho UU by delta X dabba X into delta Y delta X. And on the same line, this is for the other cases. So the two are there on the east surface. So this is in the normal direction. This is in the tangential direction. So these two velocities which is coming here in the, as the flow is in the x direction, we consider on the west surface. So the normal, tangential will be the because of v velocity and mass flow rate is in the x direction. So rho u is gives me the mass flow rate in the x direction multiplied by v velocity. So the momentum, the tangential momentum which is causing in the east surface, and this is what the normal direction. So this UU velocities are coming in the normal direction. Similarly, on the north surface on the same line, you will have this. So now we have all the on the all surfaces which are supposed to be the incoming momentum and outgoing momentum on all these four surfaces which we have. Now again we go back to the our basic equation. This is our basic equation, and now we want to consider it for the momentum. Okay, so rate of accumulation of momentum is equal to rate of inflow of momentum minus rate of outflow of momentum plus rate of increase of momentum due to any source. That is what our basic equation. So we have to use this basic equation for this incoming momentum, and this is outgoing momentum. So if you want to arrange them, we'll have the equation is supposed to be like this. Now we have started directly by considering here the x momentum equation. Okay, the reason is that we are dealing here for the different directions of the velocity, and that's why the u velocity component coming into the picture, and that's why we calling it as a x momentum equation. So for x momentum equation, u velocity is a driving velocity. In y momentum equation, v velocity is a driving velocity. Similarly, in the z momentum equation, the w velocity is a driving velocity. So again on the same line, the rate of accumulation of momentum in the control volume. So what will be the momentum of accumulation? So mass of the control volume. So mcv is the mass of control volume multiplied by the change, velocity change with respect to time. That is what we're supposed to be considering here. So mass into velocity of that rate of change of that is our the momentum change. Okay, so dabba of mcv u by dabba t is the rate of change of momentum. That is what we're supposed to be considering here in the control volume. So mass of control volume into the velocity is rate of accumulation of momentum in the x direction. And then again on the basis of the incoming and outgoing, so again if I consider this is incoming and this is on the west surface is of incoming, so this pw p dot xw and this p dot xe which is there, which consists of again this w. So incoming minus outgoing, again this get cancelled. Okay, and then you have this term which is of the minus sign. So I can consider this minus of the dabba of rho uu by dabba x delta y, and that is what is supposed to be put up here. So we'll have the dabba of dabba x of rho uu delta x delta y. Okay, this is for the x direction and this is for the y direction. So this is what the efflux of incoming minus outgoing in the x direction of momentum. This is of the efflux of incoming minus outgoing of momentum in the y direction. So we have considered the three terms. The first term is on the left hand side of the rate of accumulation of the momentum. This is what the inflow minus outflow in the x direction. This is what the inflow minus outflow in the y direction. Similarly, if I want, I can suppose to be have here the one more term, that is of minus dabba by dabba z of rho u multiplied by w into delta x into delta z. That is what we can suppose to be considered for the, and then in that case, if there are supposed to be the third direction, everywhere there are supposed to be the three dimensions are coming into the picture. But as far as volumes are concerned here, as we have taken two-dimensional case, so as it is a two-dimensional case, so delta x into delta y into 1, delta x into delta y 1 into 1, that is what we consider here for the inflow minus outflow in the x direction. And this is what the with related to the mass flux in the x direction. This is what with respect to the mass flux in the y direction. And that is what we supposed to be representing it here. Okay. And what is additional, the term is coming here is the, if I consider now, keeping these two terms on the left hand side, what we'll have is the rate of change of momentum, and is nothing but equal to the net forces. So this, the force term which is coming into the picture is nothing but the that if you see our the term which we want is that the rate of increase of momentum due to some source. And why this is coming into the picture in the momentum is because of the forces acting on this control volume. Now these different forces which we want to study, that is what our interest here. So if I take into consideration of that, so if I take into consideration of that, so we'll have on the left hand side is supposed to be the rate of change of momentum in the x direction, as we are dealing for the x momentum equation. So this is the rate of change of momentum in the x direction. This is the rate of change due to the time variant, and this is due to the space variant. Okay, so this, the rate of change of momentum, which is supposed to be equal to the net forces acting in the x direction. So this, the total force acting in the x direction can be, if I consider divided it throughout by the volume, so I will have the basic the force acting per unit volume. So we can consider here the force acting in the x direction per unit volume base. Okay, so the net force, x force acting on the material contained in the elemental control volume per unit volume basis. Okay, so this is the small f of x is indicating the force acting on the control volume in the x direction per unit volume. So this gives me the x momentum equation. Similarly, I will have the y momentum equation. Okay, so again this term only, what the change you can see as far as these equations are concerned, your driving velocity here is the u velocity for the x momentum equation. Your driving velocity in the y momentum equation is the v velocity. Just replace this on this side. So we'll have the rho v. Here will be the v velocity will be the driving. Here will be again the v velocity will be driving. So the rate of change of momentum in the y direction, which gives me the y momentum equation, and force acting on the control volume in the y direction will be Fy. So this is the x momentum equation. This is the y momentum equation. Similarly, if I want in the z direction, I will have the z momentum equation. Okay, any doubt about this?
Sir,
Yeah. I can proceed. Hello.
Proceed, sir.
Proceed, sir.
Okay. Similarly, if I want, I can also derive this by using again the RTT equation. So in this case, again, our RTT equation, the first term is the volume integral term, second one is the surface integral term is equal to the forces. So this is again from the Reynolds transport theorem, and then again using the similar laws, and we can again have the momentum equation in the vector form. Okay, so this is the for any arbitrary control volume, if I want the linear momentum equation per unit volume basis in the vector form, this is what that form is supposed to be there. So here are the x momentum equation, y momentum equation. We can further consider it to be for the vector form is also on this similar line. Okay, and now if I want to simplify it, this is again what we have. We can suppose to be want to simplify it. So the total form of this, if I want to write, so the x momentum equation in the complete form will be a dabba rho u by dabba t plus dabba rho uu by dabba x plus dabba rho uv by dabba y plus dabba rho uw by dabba z is equal to f of x. And similarly, we can have it for the y momentum equation and for the z momentum equation. So that's the way. Actually, this is the complete form of the x momentum equation, y momentum equation, and z momentum equation. Now, our interest is for the what is this forces acting on the control volume. So there are two types of forces acting on the control volume. One is the surface force, another is the body force. So we can consider this the body forces and surface forces which are acting on the control volume. So if I want to consider them, I will explain that in the next slides. So if you want to again further simplify them, so this can be further simplified as a very simple way is that if I want to write the rate of change of momentum is just nothing but like this, is that rho into du by dt. This du by dt, capital du by dt is nothing but the total derivative of the velocity. So total derivative of velocity multiplied by mass of the control volume gives me the force. So this is nothing but the rate of change of momentum in the x direction. This is for the x momentum equation for as we have taken here u velocity. If I take here small v, it will be the is equal to fy. If I take it small w, it will be the fz. So that gives me the simplest way of writing the rate of change of momentum is equal to force, and that is nothing but the momentum equations in the xyz direction. Hello, there is some noise.
प्रैक्टिकल क्विज हो गया सर, नंबर हो गया 5.
Hello, hello, there are some noise. Please, if you want to ask me question,
I have muted
you
him.
unmute, or otherwise you please mute it.
Sir, he has muted it.
Okay. So these forces which we are supposed to be considering, these forces can also be represented in the form of stress. So these forces we can consider can also be represented by the stress. So the surface forces, there are two types of surface forces, and that can be represented by the stress, such as the normal stress and the shear stress. Because we know the force per unit area is nothing but the stress. So we can represent them in the form of stress because it's good to analyze them in the form of these stresses. So normal stresses and the shear stresses. These are our surface forces, which are them in more detail that we will see in the later on. And then there is a body force. body force is which we consider the intensity per unit mass basis. That is what we can have. Now, in most of our cases, if you see that I'm not going in much details of this derivation part of these forces, what I will suggest to you, if you go from this angle also, we can analyze them in the form of that, how the fluid particle and forces acting on it we take into account, and then we can derive them. Now, my intention here is that to get the body force is in general case, we consider only as a gravitation as only the one body force, which is generally we consider acting. Maybe if I consider that this is the y direction, so the body forces acting in the negative y direction, because I consider this this is a positive y direction. So I will consider that this direction is a negative y direction. So body force only will be available in the negative y direction, unless and until there are supposed to be some system which we are supposed to be considering for the study and have some different kind of the body forces. Other than that, the body force are absent. Only one body force will be present, and that is only in the negative y direction. And then we will want to see the normal forces, surface forces. And these surface forces are supposed to be of two kinds. One is we consider the normal stress and shear stress. The sign convention for this is supposed to be the sigma xx. The first subscript of this is indicate the direction of the normal to the surface over which the stress is acting. And second subscript is indicate the direction of the stress component itself. And based on that, we supposed to be considering there. And if you want to use this nomenclature and all these things, you will supposed to be having the stress tensor there. I will not go in. Yeah, this is what supposed to be our stress tensor, which will have supposed to be there. So this sigma xx acting in the x direction. So this is the sigma xx is the normal force acting in the x direction. I will call it a normal stress or normal force acting in the x direction. This is the normal force or normal stress acting in the y direction. This is the normal stress acting in the z direction. And remaining these three group are the tangential stresses. These three are again the tangential stresses. So these two, this is DABA, this is tau xy and tau xz. Here is again tau yx, tau yz, tau xz and tau zy. So all these, what are the taus are there? These three taus here and three taus are here. These are considered as a shear stresses acting in the x and y directions and x, y, z directions, which are there in our stress tensor. So these which we want to consider. So because of these now, our equation getting to be a more complicated. And we want now all these stresses which we are supposed to be considering there to be represented in the form of velocity, because these have to be represented in the form of velocity, because our equation, if you see here, this f of x or f of y or f of z which are there, we don't know direct values of them, or these stresses are also unknown to us. Okay? So how we can supposed to be considered there? By using the definitions of the fluid, we can supposed to be use them there, and also our general laws which are there. Again, we know that the Stokes hypothesis which are there, by which we can say that tau xy is equal to tau yx, and in general we can also write it tau ij is equal to tau ji, and this is supposed to be used in our equation, and based on that which we can supposed to be put up there. So all these the equation which are the forces acting there in the x, y, z directions are supposed to be represented here. So this is the normal stress in the x direction. These are the two tangential stresses acting in the x direction. This is the body force acting in the x direction. This is generally absent, because body force in the x direction generally absent. The body force in the y direction, if I consider it towards the gravity, this will be present in the negative direction. And again, the z direction body force is absent. But others, if you see here that there are supposed to be again this sigma xx is the normal force acting in the x direction, sigma yy the normal force acting in the y direction, and sigma zz is the normal force acting in the z direction, and all these are the tangential forces acting in the x, y, z directions respectively. Now, if we want to categorize them, why these are coming into the picture? So if you want to explore this, what is the sigma xx, what is this tau yx, what is this the tau xz, and all these things that are supposed to be, we have to consider in more detailed understanding of them. And for that, what the sigma xx is supposed to be consist of. So by using this Stokes hypothesis as we supposed to be considering, and using this that the strain is proportional to the strain rate, as we are dealing here all these cases for the Newtonian fluid. So now onwards, we are supposed to be dealing this Navier-Stokes equation in particularly for the Newtonian fluid. Until now here, whatever maybe we have considered until now here is applicable for all the cases. Okay? This equation is applicable for all the cases, but now we are simplifying them to be a very specific for our case, and that is the Newtonian fluid. So in case of Newtonian fluid, we can consider this tau xy is equal to tau yx by using this Stokes law of viscosity. And by using the other assumptions, we can consider that this tau xy is equal to mu dabba v by dabba x plus dabba u by dabba y. This is what we call it as the shear stress due to viscosity. Okay? So there are two types of the surface forces. One is the surface forces which we have considered two types. One is the normal force and another is the tangential force. These normal forces are again two types. One is the pressure force and another is the normal viscous force. So this normal viscous force coming into the picture because of the velocity and viscosity in the x direction for the x momentum equation, and similarly for the other direction, as well as there is a tangential viscous force, and this gives me here the tangential viscous force. So tangential viscous force tau xy is equal to tau yx. This term, one term will be there, and second term tau xz, that is there. So again this mu dabba w by dabba x plus dabba u by dabba z. So summation of these two will be there x momentum equation. Summation of this will be there in the this and this will be there in the your x momentum equation, y momentum. First two are there in the x momentum equation. Then this x, z and z, these two are there in the your z momentum equation, and this will be there. First and third will be there in the your y momentum equation. So these terms we have to put in this. All these what are the tau terms are there. These tau terms are supposed to be replaced by these terms which are there, and what is remaining is now to have the value for this the sigma xx, sigma yy, and sigma zz, which are the normal forces acting in the xyz direction. So the value of this normal forces acting in the xy direction, as I already told you, that the normal stress consists of the two terms. One is because of the pressure contribution and second one is because of the viscous. So normal stresses are two types, the pressure force and the viscous force. So pressure force, the sigma xx is consist of two terms, minus p and plus the sigma xx, which is because of viscous effect. And then we can use this relationship by using the general Hooke's law also, and then what I will supposed to be suggest that the component of this viscous there is supposed to be sigma xx. Viscous is twice mu the epsilon xx plus lambda, the epsilon xx plus epsilon yy plus epsilon zz, and multiplied by lambda. This is the second viscosity coefficient, and then if you derive them, you will supposed to be going to get it the twice mu sigma xx plus del dot rho v. So this is again nothing but coming to be the continuity equation. Del dot rho, del dot v is equal to which is there. So I can suppose to be use this term to be represented here, right? So this lambda into the del dot v. So dabba u by dabba x plus, this is nothing but the dabba u by dabba x plus dabba v by dabba y plus dabba w by dabba z, plus what are the terms there, minus p, which is we have seen, and then this q twice mu, this sigma, epsilon xx is nothing but which we can suppose to be say is dabba u by dabba x. So if I put these terms in the our equation, and then I can simplify them. So we can have this equation to be simplified in the generalized form. So this sigma xx plus sigma yy plus sigma z is supposed to be equal to minus thrice p bar. This p bar is the our mechanical average pressure. And then if I put it together, I will have the relationship. Why we are doing all this thing? Because this lambda, which is we have used here as the second viscous term, and then we don't have the direct relation or measurement for this value. So we are trying to consider by using all these assumptions that this lambda is nothing but minus 2/3 of mu. This, or to bring this particularly, all this the part has been done, and then if I put it here, the equation is supposed to be coming to be like this. So this the left hand side is nothing but the rho du by dt. That is what the rate of change of momentum. This is supposed to be equal to this. So rate of change of momentum in the x direction, and this is the pressure force, that term which is there. So minus pressure force plus this is, I have just simplified. We can derive it by what the definitions which I have used in the previous 3-4 slides. So if you use that definitions of each of that terms of the shear stress as well as the normal stress, and if you simplify them, you will getting here it in the form of the mu dabba square u plus dabba x square plus dabba square u plus dabba y square plus dabba square u by dabba z square, and this plus this term is coming into the picture plus the gravitational force. And if I put this in the form of the vector form, I will have this the generalized form. Now here you will have only the velocity, and this is the pressure term. But still, if you see like this, if you go into the details of them, these terms are coming into the picture. And then if I again further simplify them, I will have for the inviscid flow and for the incompressible flow, the simplifications can be done. So if you see the previous equation, there are these two terms of viscous forces are there. The second force will be gone if I consider that it is a incompressible flow, because I know in incompressible flow del dot v is equal to 0. For incompressible flow, density is constant, and because of that density is constant, we'll have del dot v is equal to 0. So this term will be gone for the incompressible flow. So we'll have only the minus p plus mu del square v plus rho g. These three terms will be there on the right hand side for the forces. So pressure force plus viscous force plus body force, these are there. So okay, so pressure force plus viscous force plus body force, this will be there for the incompressible force. And if I consider the inviscid flow, so viscosity is absent, and that's why only two forces will be there. One is the pressure force, another is the body force. This equation is also known as the Euler equation. Okay. So this can be supposed to be further we can use for the derivation, and we can put it in the different form. Okay, and this can be used to derive the Bernoulli's equation. And on the similar line, what I have supposed to be considered, let us say for the basic, again we go back to our basic equation. This is our basic equation. So what we have tried here to consider that the derivation for the continuity equation. So using this basic statement, we have tried to derive it for the continuity equation. The rate of accumulation of mass, which is on the left hand side, is equal to rate of inflow of mass minus rate of outflow of mass plus any increase of mass. We have not considered this term for the mass because there is no any when we consider the mass generation is not there. The mass generation is only considered in the nuclear reactions. Other than that, generally the mass creation is not considered. So there is no any the mass increase due to any source in the given control volume. And then we consider the second case, that is of rate of accumulation of momentum. So rate of change of momentum, we consider these three terms are taken together, will give me the rate of change of momentum is equal to net forces acting there. That is for the second equation. And now I want to consider for the third equation, and that is what the energy equation. So rate of accumulation of the energy, which is supposed to be, we can equate to the rate of inflow of energy minus rate of outflow of energy plus rate of the increase of energy due to any source. Again, it is on the same line, which we can suppose to be considered to be derived. Now I will use the statement which is supposed to be the more commonly we are using. So if you see here, I have tried here to represent all these governing equation in the very generalized form. Okay, so I will take it again. Pointer, yeah. So this is our generalized form of the governing equation. Okay, so we can represent all these equation in the form of our mass continuity equation, momentum equation, and energy equation. Now, to represent them, what we have supposed to be considered. So I have used here the continuity equation for the two-dimensional incompressible flow. So for two-dimensional incompressible flow, the continuity equation is dabba u by dabba x plus dabba v by dabba y is equal to 0. That is what we have already derived. For x momentum equation, again I have considered here for the two-dimensional, okay, two-dimensional incompressible flow. So we have here dabba rho u by dabba t plus dabba rho u by dabba x plus dabba rho u v by dabba y is equal to minus dabba p by dabba x plus mu dabba square u by dabba x square plus dabba square u by dabba y square. This is x momentum equation. This is the y momentum equation. So if you see here for the x momentum equation, u is our driving velocity. So this is what kept in the square blocks of u. Yellow square box. V velocity here kept for the y momentum in the square box. Similarly, energy equation, the temperature kept here in the square block. Okay, so these three which we have considered here. So u velocity is considered as a driving velocity for the x momentum equation. V velocity is considered as a driving velocity for the y momentum equation. W velocity can be considered as a driving velocity for the z momentum equation, and for energy equation, temperature can be considered as a driving velocity, driving value, that is a driving temperature we can suppose to be considered. So if I want to represent all of them in the generalized form, so I have here the generalized equation. I have represented them in the form of the variable phi. So dabba rho phi by dabba t plus dabba rho u phi by dabba x plus dabba rho v phi by dabba y is equal to gamma phi dabba square phi by dabba x square plus dabba square phi by dabba y square plus s phi. So this is what our general form of equation, and then I can put it in the different value. Like I can consider phi is equal to u for x momentum equation, phi is equal to v for y momentum equation, phi is equal to t for the energy equation, and this phi is equal to, if I want to consider the continuity equation, what will be this phi value? Anybody? Anyone? What could be the phi value for the continuity equation?
It is answered in the chat box, 1.
Okay. Thank you. Yeah, it is supposed to be 1. Okay, so the value of phi will be 1 for the continuity equation. Okay, so our driving velocity will be for x momentum equation, u velocity, v velocity, and temperature for energy equation. And what are the source terms which we have there? This is minus delta p by delta x minus delta p by delta y, and this is the for the energy equation is the heat generation. So volumetric heat generation, that is what supposed to be our, here is the, these are forming our governing equation, and this the gamma phi will be equal to mu for the momentum equation and k by Cp for the energy equation. And that's the way we can supposed to be consider that these equations we can write and form here as a generalized form of our governing equation. On the same line, which I have supposed to be tried to explain you, we can derive it for the different cases. I think I am. Is it okay, or I could have to explain anything more detailed? Anyone?
Yes, sir. What is the question you said?
Do you want any more explanation about all these the governing equations, or
Maybe
is it okay?
you can,
what
you
we have
can
discussed?
maybe you can talk about the boundary conditions and initial conditions
Yeah.
while solving such kind of equations.
Uh,
Mathematical character.
I think that okay. So if you see here, in continuation of that, we have here the boundary conditions. If I
Sir,
consider now the boundary conditions, so
sir, your presentation is not
hello,
visible.
is it now?
No, your presentation,
It is not there.
no, it's not there on screen.
Slides are not visible, sir.
Now?
No, I think you have to go to stop sharing and again share it.
Okay. I will do that again. Is it now?
No. No, your slides are not
What
visible.
happened? It's sharing is disabled.
You have disabled your sharing.
Yeah.
Go to share and then
Just a minute. Yeah. Just a minute. It's not showing me any. Why it is happening? Now it is visible.
No slide.
The slides are there now.
No. I think you have
No, sir,
minimized it.
not it.
Not yet. Oh, what happened? I will close all these and then I will again open. It's not showing me all this. My window is shared.
Majid, back.
So we can see your window, but
Majid, back.
your presentation is not
laptop
visible.
Okay. Okay, what is happening? I have to see. I have not given. Now what happened? I didn't understand. Oh.
Sir, we can see your shared window, but your browser is open. So minimize the browser, then open the presentation.
Now? Now? Mhm. What happened now? I'm not getting.
Sir, minimize the browser, right, sir? Yes, sir. Now it is visible.
It is
Okay.
visible.
Thank
now.
you.
It is visible.
Now?
Yeah.
Okay. Sorry. There are some always when we take online, we are very new to all this. Sorry. So if you see here, I have here the conduction equation. This is the considered to be the two-dimensional unsteady with heat generation equation. Okay, conduction equation. So it is a two-dimensional, as these two are there coming into the picture. So it is a two-dimensional, and this term is coming because of the unsteady term, and this term is coming because of the heat generation term is there. So what are the equation which we have seen here? This generalized form of equation. I consider this the energy equation first. So that we can have the boundary conditions and initial conditions to be applied for solving the generalized form. So when we start with any problem solving, and let us say I want to solve now for the conduction equation. So conduction problem which we have, and let us for the simplicity I have taken, let us say that the two-dimensional unsteady with heat generation is the case. Okay, so the plate, as I'm mentioning, it two-dimensional. So I have taken here one plate. So this is my one plate, and this plate is two-dimensional, so having the delta x and delta y are the distance in the x and y direction. So this is, I will take again, sorry. Yeah, this is the delta x distance, and this is the delta y distance, which is I have, let us say, for this plate. So west surface, this is the south surface, the east surface, and north surface. This is which we have here for the plate. So two dimensions which we have supposed to be considering. Now I'm considering that the it is unsteady, and that's why this term is coming into the picture. And if I consider there is some source, heat generation is there. Let us say that the electric heater is there, which is in, kept in the between on this plate, and that heater is having the volumetric heat generation. So if I assume that the case, the governing equation will be simplified to this. So on the left hand side, you will have only one term, that is dabba rho by dabba T. If you see the previous equation, out of this, the generalized form, this is the only term will be there. Why these two terms are absent? Anybody? This is called as convection, as problem which we are dealing in conduction problem. So these corrections are up. These are being velocity. As far as the conduction problem is concerned, no velocity, no u velocity, no v velocity. So these two terms are absent in the conduction equation. So we have the first term equal to this term, that is a diffusion term, the conduction heat transfer that is there, and heat generation. So the three terms are only there, and that is what is supposed to be represented here. So this is the unsteady term, this is a diffusion term, and this is the source term. And multiplied by here, what we have is the alpha, that is nothing but the, because of, if you see here what is coming here, that the rho is coming there, and K by Cp. So this is nothing but coming because of the thermal diffusivity. Okay. So if I take into consideration of that, this is my governing equation, and now I want to apply the boundary conditions for this. Now, as this time term is coming into the picture, we have to give it in the initial condition form. And that is what, at any particular time, we have to give the values for all the control volume which we have supposed to be considered here. So if I take that t is equal to 0, that is my, let us say, the time. So t is at any particular interval. Now I have taken here t, x, y, z, but as far as our case is concerned, it is t, x, y is equal to t0. So at time t is equal to 0, all the temperatures at all the nodes or all the control volume cell centers, whatever may be the way we are solving this, whether you solve it by the FDM method, that is finite difference method, or you solve it by finite volume method, or you solve it by finite element method. Whatever may be the method you use for solution, when we have the initial condition are supposed to be given, or if it is a time marching problem, I will call it as a time marching problem, we have to give the values to each and every control volume cell centers or nodes or whatever maybe we are considering there. So that values are supposed to be at t is equal to 0, t, x, y is equal to t0, whatever maybe you call these values, or t0. Okay, that is what the initial boundary condition. Now, as far as this conduction problem is concerned, we have here the 4 boundary conditions. I'm calling here, these are 4. They are actually 3, but they are supposed to be taken as a 4 also. Now, first one is considered here as a Dirichlet boundary condition. Dirichlet boundary condition means which gives me the fixed value for this particular surface. Okay, so what I have considered that for this particular left surface, which we have on this plate, have the Dirichlet boundary condition. And the beauty of this boundary condition is that we don't have to do much about this boundary condition. The temperatures, as far as this conduction heat transfer is concerned, the temperatures are directly available to me on this boundary. So let us say 100 degree, 200 degree, 300 degrees Celsius, whatever maybe you want, these temperatures are directly available on this boundary. Okay, and that is the beauty of this Dirichlet boundary condition. So when we have the Dirichlet boundary conditions, the temperatures are directly available at the boundary of it. Then second is the Newman boundary condition. Newman boundary conditions have two types. One is that the dt by dn, n is the in the normal direction. Change in temperature in the normal direction is a constant, which is known as the Newman boundary condition. Now, if I assume that this constant is 0, then that plate is considered as an insulated one. Okay, this plate is considered as an insulated one because of this, the boundary condition in which the rate of change of temperature in the normal direction is 0. That means that the adjacent layer of this control volume is supposed to be considered have the same value at what we have at the boundary condition. What I mean, if let us say I consider this particular node cell center and this particular node cell center, the values are same. They are the normal dt by dn. If you take the normals here, so dt by dn at this surface is equal to 0. And that is the condition used particularly for the insulation. So in insulation, we have that the normal direction change in temperature is 0. Whereas on this, the right hand side, we have this with some constant. What it means that some constant heat generation is coming on this surface. Okay, so because of that constant heat generation, let us say that some heater is on this surface, and that heater is constantly giving some heat input, and that considered here as the C is equal to minus QW by K. Now this K will be depending on what is the thermal conductivity of this plate. Okay, based on that, this Tt by dn, so change in temperature just adjacent to this boundary. Okay, the change in temperature just adjacent to this boundary will be governed by this Q by Kw value. So this minus Q by Kw value will be govern the change in temperature in the normal direction at this particular the east surface. And the fourth one, actually these two I have supposed to be considered, and then the fourth one is known as the Robin or mixed boundary condition. And this Robin or mixed boundary condition is supposed to be considered based on that the conduction heat transfer is equal to the convection heat transfer. Now what we are presuming that for this particular boundary and just adjacent boundary which we have there, the conduction heat transfer which is taking place from that adjacent layer to this boundary surface is equivalent to the convection heat transfer from this boundary surface to this environment may be there, or some another fluid may be there, or water may be there. The fluid system might be there, and that fluid system having the thermal having the coefficient of the convective heat transfer coefficient H, and the temperature of that environment, let us say T infinity. So we have supposed to be considering that the conduction heat transfer from the adjacent layer to the boundary surface is equal to the convective heat transfer from this boundary surface to this surrounding, and that is what is represented here. So Q conduction is equal to Q convection. So Q conduction is minus K dt by dy. So the change of heat in the y direction, as we are supposed to be considering here. So the just adjacent layer to the boundary surface, so water may be there, that we take into consideration here, is equal to H into delta T. So this T is the temperature at your boundary. Okay, this is the temperature at boundary which is unknown to us, and this T infinity is the temperature of this environment. What is maybe you consider any fluid may be there, you may have some water there or some air there or some water, maybe another fluid which Any fluid can be here, and having the H is the convective heat transfer coefficient of that. So H into delta T is equal to minus K dt by dy. So if I use this basic definition of this for this boundary condition, I will have this equation, and out of that, this T is unknown to me. So this T is unknown to me, and this T will be depending on this three different parameters. One is what is the value of this K, what is the value of this T infinity, what is the value of this H. Okay, based on that, this T value, which is at the boundary of this control volume, will be there. Again, this value is also going to change because what are the changes are happening at the adjacent layer also. So the value of this at this boundary is not always supposed to be constant. It is varies with all these different parameters. Similarly, on this surface also, on this each surface also, the values are not constant. It will be varies depending on what is the value of this Q generation and what is the value of this K. Similarly, on the bottom side also, these values are again not constant throughout the surface, but they are constant in the normal direction to the adjacent control volume cell centers. We'll see that when we deal more detail in the any conduction problem in next lecture tomorrow. This is as far as the boundary conditions for the conduction case are concerned. Similarly, we can have the boundary conditions for the fluid flow problems also. No slip condition, free slip conditions, and any inlet conditions, and like this. Non-dimensionalization is also the very important to be considered. So all these equations which we have derived actually can be considered into the non-dimensional form also. Not consider it here. I thought it will be required, but you can derive them. What are the equation we have considered? The continuity equation, momentum equation, and energy equation. These can also be considered for the non-dimensional form. Any question? Anything? I think 4 o'clock is there. This is from my side. If you have any doubt, any question.
Sir, there were few questions which I have answered in the chat box. The participants still have some questions. Please go ahead. I mean, you can ask the questions verbally.
Yeah, actually, I was unable to see the chat box when I was.
No, I answered it in the chat box.
Okay. Okay.
There is a question how to select the number of boundary conditions. Shall I answer this question?
Yeah, you can.
See, if you look at the mathematical character, then depending on the directionality of the problem. If your problem is one-dimensional, you need to have two boundary conditions at least. If your problem is two-dimensional, you need to have four boundary conditions. And for three-dimensional, you need to have six boundary conditions. So that's a simple thing, simple logic you can adopt. And then boundary conditions are of three types: Dirichlet boundary conditions, Neumann boundary conditions, and the Robin boundary condition. In Dirichlet boundary condition, your variable is constant on the boundary. In Neumann boundary condition, your derivative of the variable is constant on the boundary. And in mix or Robin boundary conditions, both the things are combined together. So for number of boundary conditions which are required, that usually depends on the directionality of the problem only. So if you have d2t by dx square is equal to 0, that's one-dimensional heat conduction equation. We need two boundary conditions. There is another question. Is there any limit on the initial conditions? See, if your initial conditions are strong enough, I mean, very close to what is happening, then you can have a better solution, and you can have a quick solution also. So initial conditions are actually the actual conditions. Actually, it's not initial case. If your problem is intrinsically unsteady problem, then you must have a proper initial conditions. I hope, Mr. Robo, I have answered to your questions. Am I? Mr. Rana Robo?
You can start for the any initial condition also, but the in that case you need the long. The calculations can be a very long or something which will be take more time in the computation or something like that. So it is always supposed to be the also the judgment from where we can consider the initial conditions.
See, he has another question. If I have a second order 2D problem, how many boundary conditions are there? I mean, for 2D problems, as I said, 4 boundary conditions. For 2D problems, we have a second order equation only, second order differential equation. Okay. Is there any question, by the way, from the participants? There are no questions. Maybe there are no questions. Maybe we will stop.
Okay, thank you very much.
I express my sincere thanks to Professor M.R. Nandgaonkar for dealing with governing equations. Governing equations are fundamentals in nature, and if you have a physical understanding of the governing equation, you will be able to have a better definition of your problem. I mean, if you open any journal publication on fluid mechanics and heat transfer, you will find in the problem definition, the first thing which is given is our governing equations. You must be able to write your own governing equations. The moment you know the governing equations, you can then decide the physical boundary conditions, initial condition, and so on and so forth. So thank you very much, Professor Nandgaonkar, for sharing your valuable time and valuable inputs, valuable knowledge.
Thank you very much.
This will definitely be helpful to the participants in general. Thank you very much. So we will break for today now, dear participants, and we'll meet again tomorrow at 10 o'clock. At 10 o'clock, we will be starting with the actual finite volume methodology for 2D heat conduction problem. Again, Professor Nandgaonkar will deal with that. And then in the afternoon, I myself will deal with the unsteady state problem. And Professor Chaugule will tell you how to use the software for solving simple problems. So thank you very much.
Thank you. Thank you all.
We will be leaving the meeting now. Thank you all.